Hi, in this video I'm going to focus on type 1 and type 2 errors. These are the scenarios when you reject or don't reject the null hypothesis, but they might be true and they might be false, right? So we have 4 scenarios here, and 2 of these scenarios are correct outcomes. That's basically when you reject the null hypothesis when it's false, meaning that you need to reject it, okay? You did what you were supposed to, you did the right thing. And when you don't reject the null hypothesis when it's true. So here, the null hypothesis is true, and you failed to reject it, meaning that you came to the right conclusion, right? There are 2 other scenarios when you commit some sort of error here. So we have type 1 error, and that's when you reject a null hypothesis when it's true. And then you have type 2 error, which is the case when you don't reject the null hypothesis when it's false. It's basically when you can't reject that a criminal is innocent while the fact that he's innocent is false, right? So this is called beta. We've gone through alpha, and alpha is always an essential part of our procedure when we do the hypothesis testing, but beta is the new here, and I'm going to go through some examples concerning it. Here's a conceptual example. So when you have the null hypothesis here as the process is satisfactory. So when the type 1 error in this case, which is also known as the producer's risk, the producer is looking for a problem that does not exist, because we always reject that null hypothesis. The process is satisfactory, meaning that we're supporting that it's not satisfactory, and we're trying to look for a problem that is not there, all right? So that is one of the examples, and it's as the book says, it's known as the producer's risk, because most of the time when we read that null hypothesis, you are allocating resources and time and dedicating that to trying to find where the problem is, even though it actually does not exist, right? Well, when the process is actually not satisfactory and we fail to reject the null hypothesis that it is satisfactory, here the risk is on the consumer's end. So they actually take that part. So once you're producing those products using these processes, it's on the consumer's hand. Now we fail to reject that this process is satisfactory, while it's actually not. So what happens here is that the customer is getting a product from a process that is not performing properly. But then the question here is, how do we actually consider the 2 types with like when doing hypothesis testing at the same time? So the book suggests this, that we need to decide on a value for alpha before selecting the sample, which makes sense. And then once alpha has been set, the value of beta can be calculated. So you first decide what's your alpha, and given that, you calculate beta. And this is very important here. Well, you have to know that for a given sample size, reducing the value of alpha will result in an increase in the value of beta, or the opposite. So the only way to reduce simultaneously is to increase the sample size. I'm sure you've heard it now many times throughout the course. Increasing the sample size is always positive. It helps us with the central limit theorem, and it helps us with reducing variability, and it will help us also here. And here's an example using numbers. So in this example, a scientist wants to test whether the average daily spring temperature has increased from an average of 50 degrees in a prior year. So the null hypothesis is that it didn't, so it's actually 50 or less, but from past information, she knows that the population standard deviation is 6 degrees. And she plans to test with an alpha of 5% using a sample of 64 days, right? So suppose we fail to reject that hypothesis, meaning that we can prove that the temperature has increased, when in fact the true mean now is 52 degrees. What's the probability of type 2 error? So the type of questions we have when we involve type 2 errors is that we always assume a value for the population parameter and calculate the probability from there. So we would say, what would be the probability of type 2 error if the true value was this or was that. So I know this might sound like not the straightforward way of answering those questions, but it's at least a way to do that sort of risk calculation for that type of error. All right. So here's how that looks when we graphically represent it. So we have this original hypothesis, and with the assumption that we have the claim here that the true value is 50 of the temperature, while the true value was 52, right? So that's the assumption here, that it was 52. So here, as you can see here, on this graph, we could reject a hypothesis, 5% that lies in the rejection region. But if we project that on the 52 graph here, when we have 52 as the mean, as the population mean, we see that, well, this whole region is inside the don't reject region. All right, so we don't reject. So when we reject the null hypothesis here, we fail to reject the null hypothesis having this as an assumption, right? Having 52 as an assumption for that type of temperature, all right? So the green part here, the green region, is what we call beta. So this one is alpha, this one is beta. So you can see why increasing the area under the curve for alpha here would mean actually reducing the area under the curve corresponding to beta. And here, beta is going to change depending on the assumption of the true value of the population mean, right? And as you can see here in the statement, beta is the probability that we don't reject the null hypothesis if the mean is 52, right? So the mean is 52, and the hypothesis testing we did here was based on that it's 50. Then we have beta as corresponding to this region here. Okay. So with the inputs in mind, we have something that we're introducing here, and it's actually not that new if you think of it. Well, this is the critical sample mean. So we have the critical z-scores or the critical t-scores, and these basically mark where the don't reject region is located. So from that to that, if it's a two-tailed test, or if it's a one-tailed test, then it's a specific z-score that we call z-critical or t-critical, depending on if we know the population standard deviation or not, right? So for that z-score, there is a corresponding sample mean that we can calculate, right? So all we need is just the standard deviation, or the standard error if we don't have, or the sample standard deviation if we don't have that. So as you can see here in this picture, you see that we have that formula, and that's basically plus or minus because we use the standard deviation to actually find it, to find that on both tails. Well, this example is just an upper tail test, so we just take the plus sign in this case. So we'll just apply the values of that, and that would be the null hypothesis, the hypothesized average temperature of that population, which is 50, plus the z-critical that we calculate using Excel. That will be corresponding the 5%, having the upper tail assumption, of course, in the background here. And then we have the standard deviation divided by the square root of the sample size. So that would give us a value here that's going to be 51.23. So after that, so any higher value than this is going to, if we take a sample and we get any greater value than that, we will reject the null hypothesis that this is 50, that the average temperature is 50, okay? Because that is where the border is, the border of the rejection region is. All right. So why did we calculate that? As I showed you earlier in the one of the previous slides, is that we need this value here since it marks where the beta ends. So we know that beta is going to end here. It starts, the rejection region here starts from this value. So to be able to calculate beta, we need that value to project it on this curve, on this 52 bell curve shape. So this is also a normal distribution. It's just the only thing that is different here is that we have a 52 as an assumption instead of 50. and we assume that this was true. So we just need to find the corresponding z-value for the 52 on this curve. So having this as a mean, what would the z-value be if we project it? So now we're not looking at that. We've just taken this value from this curve to be able to use it to calculate the z-value, the corresponding one, having that curve in mind. So all we need here, we're going to use the same parameters. We're just going to change this. So now you can see that, well, this is going to be actually a minus, because here it's not on the upper tail, it's on the lower tail of this, because 52 is greater than 50. So the z-score here will be minus as we calculate it. So just to remind you, well, the formula is that the sample mean, so usually we use the sample mean, but here, since what we want here is this critical sample mean, so we use that critical sample mean minus the assumed or hypothesized mean divided by 6, and that's the standard deviation, divided by the square root of the sample size, right? And then we get the z-score, which is in negative in this case. So knowing that z-score, we can calculate the probability, which represents the area under this curve. And since this is a normal distribution, we just use the normal distribution. We input this z-score to get that probability. And then that probability is going to be beta, basically. So this is how we calculate beta. And this is to show you how this calculation looks like. And here we introduced what we call the power of the hypothesis test. So that's the probability of it correctly rejecting the null hypothesis. So the formula is super simple. It's just the 100% minus beta. So that's basically the reverse or the opposite of what beta is, the opposite of that. So if the power is, in this case, we had our beta from this example is 15%. So the power of the hypothesis test in this case is 84% or 85. How do we interpret this? Well, as the true population mean moves away from the hypothesized mean, the power of the test increases. Okay? This makes it easier to correctly reject the null hypothesis. And you can think of it this way. Well, if we have very small beta, this means that we have a high number of alpha. So if we have 20%, alpha is 20% in this case. Well, this makes it more easy to reject the null hypothesis if our sample is just a little bit far from the mean. All right? So when the true population mean is so close to the hypothesized mean, the power of the test becomes very small. And that makes it really difficult to accurately reject the null hypothesis. And if we come back to alpha and take that into the picture, we'll see that, well, alpha would be something like 1% and beta would be something like 50% or so, and the power of the hypothesis test will be 50%, right? And there is a power curve here that you can use, and that curve plots if you change the assumed true value for that population. In our case, we had it as 50, right? Remember? But then we had 52 as the assumption of the true value of the temperature. But we can test, if we had that as 47, what would the power value be? And then we repeat that on several situations here, just to see how the curve would look like. And you'll see that, well, as you go far from 50, we see that the power increases, meaning that it will be easier to reject the null hypothesis. Some concluding remarks here. When we reduce alpha, the value of beta increases, and vice versa. And this graph just shows you why would increasing the sample size have a positive effect on both, meaning, when I say positive, well, by reducing that, so it's basically a negative effect. So reducing these errors or the risk of having them by increasing the sample size, because the shape of the curve is what changes when we increase the sample size. It gets more curved inward, and this whole area is basically reduced. And finally, for the same calculation of type 2 errors when we have proportions, we follow the same procedure. The only difference is how we calculate. Instead of calculating the sample mean critical, we calculate the proportion critical. So it's the same thing, everything is the same, only difference is this formula, and that's basically the corresponding one to the one I showed you earlier here. So this one. So the critical sample mean, that would be the critical sample proportion. All right. So before I end with that, I would like to show you the template that I uploaded on Canvas that you can use. So as you can see here, the template shows two sheets, and the first one is concerning the type 1 error, and that's basically the standard hypothesis testing that does not consider type 2 error. So all the questions that we've gone through should be used, or should be appropriate or suitable for this template, for this sheet. And here, as you see, well, these are the scenarios when we know the population standard deviation with the one-tail test, upper tail or lower tail, or if we have a two-tail test. And this has the corresponding hypothesis statement, as you can see here. So that should be enough guidance for you to know what to use and how to use it. And then you have when the standard population standard deviation is unknown and when you have proportion. And then you have the other sheet when you have inputs corresponding to the examples that I showed you. So here you can see a one that is dedicated to proportions and the calculations of that, and the one that is related to the population mean, or population mean as the population parameter. Okay, and here we have also all the three scenarios in each of these main scenarios. So let's assume that temperature example, when we had the claimed population to be a 50, so is it like 50 degrees, and then the true population mean to be 52. The standard deviation was 6, and the sample size, I believe, was 64. I'm gonna check that again. Yes, it's 64. And the significance level was 5%. So we're looking at a one-tail, upper tail test. So Z critical here, or the Z critical is going to be 1.644. So we got one to calculate the critical sample mean. So that would be, as you can see, you can get that straight away. Here is that the null hypothesis will be rejected for any sample size proportion, sample mean that is, this is incorrect, it has to be actually sample mean. So for any sample mean that is greater than 51.23. Curve, as you can see here. Well, in this case we have this as but as we increase that range or different so if we say, for instance, we have this as 51 instead, so we're coming closer, so sorry, 51 on the true value here. This number, this power, is getting smaller, and that's because we're making these two closer to each other, making it easy to reject, more difficult to reject the null hypothesis. Far from that, by 53, this number is now 99%. Very easy to reject the null hypothesis. On Monday or in the next class, we'll have a quiz about this part, so be prepared for that, and see you then.